Department of Civil Engineering at NIT Raurkela. He has completed his PhD from Anna University. He has published more than 94 articles in different international and national journals and conferences. In addition, he has successfully guided more than 12 doctoral students and is presently mentoring several others. Dr. Singh has been honored with numerous awards for his outstanding achievements. With due respect, I now invite Honorable Dr. Suresh Prasad Singh sir to kindly address the gathering. Please, sir.
Okay, thanks, Dr. Meena and Dr. Subhasri. So for
Samya.
your kind, Soumya, for your
Yeah.
kind words. So it is my pleasure to share some recent developments in geopolymer area. And before that, it's a very good evening and happy New Year all the participants. As I came to know that there are many young participants are there. So my presentation for coming 1.5 hours will mostly focus on this geopolymer, its sustainability aspects, and I will touch a little bit on the geopolymer concrete. And specifically, I like to share that I'm a professor and head of civil engineering department at NIT Raurkela, and my specialization is geotechnical engineering. But my first student is Dr. Meena Murmu, who is the coordinator of this course. So she is from structures, and she like to work on a topic which will be helpful in your career. So she started to work on alkali activated concrete or alkali activated material. And from that day, some of my students, they used to work on geopolymer, its synthesis part, and more on this application of geopolymer in geotechnical engineering, stabilization of weak marginal soil and all these things. So with that background, I will be sharing or I'll create an interest with the young participants about the geopolymer and its at the present scenario, what is the research and a little bit more, not deep into the concrete in this one. But if you like, you can have a discussion on concrete if time permits and all these things. So with this one, shall we start with whether if the participants are joined, most of the participants, we can start with our presentation. Is it Dr. Meena? It's all right?
Yes, sir. Yes, sir. We'll start.
We'll start. Okay.
Yes. Participant will join. Maybe we have started late that link.
A little bit, but we have finished in time because one more
speaker is there.
Speaker is there. So I'll try to finish my presentation within the time. Okay.
Thank you, sir.
Then just share it. Okay, is the slide is visible to the participants?
Yes, sir, it is visible.
Okay. Okay. Once again, good evening to all. So my presentation will be on this geopolymer and alternative eco-friendly binder to Portland cement. So I have compiled the works of recent works of my students. But before that, we'll go what is the geopolymer and its synthesis and the factors influencing this synthesis and all these things. We'll go step by step. What is the next one? This one. Okay. Okay, this outline of this presentation will be touching upon the history of conventional binder, necessity of eco-friendly binders, introduction to geopolymer, raw materials required for the synthesis of geopolymers, then geopolymer mechanism and structure, factors influencing geopolymer mechanism, advantages and disadvantages of the geopolymer, and research on this area. So coming to that history of conventional binder, so the conventional binder, what you civil engineers use in our construction is the OPC, ordinary Portland cement, and it is extremely used in our construction industries, and it is the second abundantly used material next to water, and the annual production of OPC is about 4.1 billion tons in 2023. And if you see that the increase of OPC from 1995 to 2023, it is around 1.3 billion tons to around 4.4 billion tons of, and the demand of cement is increasing day by day because of this infrastructural development and associated activities. But the problem with that OPC, despite huge demand, it causes several environmental impact. Environmental issues are related, serious issues are related with this production of OPC. So coming to that global production of OPC, this is your conventional binder. China is 52%, India 6%, Japan 1%. Then this in all together in these Asian countries, it is around 80% of the cement production, and all other continents contribute only 20% of the cement construction. India also, we have a major share of 6% around cement consumption, next to China and all these things. And if you see that production process of OPC, is it sustainable or not? So can you tell what the material we are using as a civil engineers in our construction is a sustainable material? So focusing this one, I'll tell that for production of cement, huge mining is required of natural resources. Like we use limestone, dolomite, natural clay. These are the ingredients we use for manufacture of cement, which is not a renewable source, because once the limestone or dolomite exhausted, it will be exhausted. It is not a renewable source of material. So huge amount of natural resources mining this one, and it is accompanied with high energy consumption. The energy consumption for 1 ton production of OPC is around 3.5 to 4 gigajoule of energy. Huge energy we require. And to get that energy, we burn fossil fuel, coal, or petroleum products we burn to get the energy. Then high emission of greenhouse gases. And it is said that about 0.85 tons of carbon dioxide is released for production of 1 ton of cement. And what is the present cement production is 4.4 billion tons annually. That means around 4 billion tons of carbon dioxide we are releasing to atmosphere, which causes a great concern to our environment. And the cement industry only is responsible for 5 to 8% carbon dioxide emission globally. So we contribute to this production of cement contributes about 5 to 6% carbon dioxide to the total carbon dioxide emitted emission to our society. Then coming to these characteristics of sustainable manner. So we are talking about the sustainable development, sustainable material, and we civil engineers, we are more concerned about the sustainable construction material. So what do you mean by a sustainable construction material? First of all, any material which we use in our construction should meet the structural needs. So any material, whether used in any structure, maybe a RCC structure, maybe a geotechnical structure, maybe any structure what you construct, it should meet the structural needs. That is the strength and durability. This is the first aspect. Unless otherwise, the properties which we are essential for the structure, if it is not met, that material we cannot use in our construction. So first is that it should meet the structural needs. We should not have any compromise with the strength and durability of the material which we'll be using in our construction. So second aspect is the use of eco-friendly material and renewable material. So the material which we'll be using in our construction should be eco-friendly and renewable material. Like suppose sometimes we use steel reinforcement or reinforcement bars, which we got from the iron ore. Iron ore is not a renewable material because whatever the deposits are there, if it is exhausted, so we'll not get iron ore. But instead of that, if you go that bamboo strips, sometimes we use the bamboo strips as a reinforcement material. So it is a renewable material. We can produce these bamboo strips for reinforcement and many other things we can see. Next is the promotion of waste reduction. So our industrial process generates huge amount of waste or byproducts, which is being dumped in our locality or in the industrial areas and attracts the pollutions. So as far as possible, we should have a technology or material, develop a material which uses the waste materials so that the problems associated with waste disposal will be solved and we'll get a much valued construction material. So our focus should be on also the, as far as possible, the utilization of byproducts or waste. Then it should be energy efficient. This is one of the bigger, most of the industrial process or manufacturing process, it is energy intensive. So we should reduce the consumption of energy. And mostly we got the energy from now at present is fossil fuels. So that also creates problem to the environment. So a good sustainable construction material should focus on the energy efficient material. Then economy in construction. So it should be with less cost. The material should not be, it should satisfy all the requirement and the same time it should be economic criteria should satisfy. Then next is the use of local available material. Also, we should focus on the local available material so that transportation and other cost will be reduced. And nowadays, one more concern is the water, scarcity of water. Previously, you don't bother about the water, use of water, but now there is a scarcity of water. So the process and should be water efficient. As less as possible, we'll use water in our construction or development of our new material. So keeping this thing in view, so this is a chart showing the importance of this one. So you have a societal need. For civil engineers, societal need is the construction material. We, the civil engineers, use most of the natural resources in our construction. So our constructions are huge and big. So if you construct a pyramid, so it will be appreciated. It is a very big structure, huge structure. If you construct a Bruce Tower, it will be appreciated. And particularly road, rail network, embankment, dam, huge material we use, we consume the material. So the civil engineers, they consume the natural resources abundantly. So we are the civil engineers, so we have to see that how this natural resources, use of natural resources to minimize. But keeping this one, our construction activities should not suffer. So there is a societal need and there is a restriction. So that has to be balanced by a societal need and our construction material. Then next is the coming the environmental concern. So once you are using a material in our construction, civil engineering construction, it should be environment friendly. It should not affect the environment much. So environmental impact should be the minimum. First, we have to meet the need of the society. Second thing is that it should not affect the environment or pollute the environment, bad effect on the environment. Third is the economy. There is a economic. This material what we will be developing should be economic, so that the project cost will be there. But after all, the sustainability. The most important is the sustainability. So keeping all these things, we have to develop new material or in our construction or technology so that is there anything? Okay. So it should be like this one. You should focus all these 4 points in our construction. So, okay. Next, how will you go? Okay. Okay. Then, okay. Then coming to the geopolymer. This as the term indicates, no, it is a geopolymer. It has 2 terms. I can divide it with the first is the geo, next is a polymer. So it is a polymer which is derived from the geomaterial. So a polymer which is derived from the geomaterial, we call it geopolymer. So what do you mean by a geomaterial? Geomaterial which is produced from or which is obtained from the earth. So soil, rocks, everything we call the geomaterial. And a polymer which is synthesized or produced from a geomaterial, we call it geopolymer. So geopolymer as defined as the inorganic amorphous to semi-crystalline 3D frameworks comprises of silica and alumina tetrahedral units linked with covalent bonds. Okay, so it is first invented in 1978 by Joseph Davidovits. This term geopolymer is coined by French scientist Joseph Davidovits. So if you see that geopolymer, I told you the geomaterial, all soil. So what is the chemical composition of a, if you see that chemical composition of a soil or geomaterial? So it is nothing but it is a aluminosilicate, mostly except few ores, minerals, most of the soil, it contains aluminosilicates. A major portion of the soil is aluminosilicates, alumina and silica material. So geomaterial is nothing but it is a aluminosilicate materials. So can you use the natural geomaterials or soil in our synthesis of geopolymer? It is no. Why? So how it is produced is it is produced from alkali activation of aluminosilicate waste material. So we'll be using the geomaterial not directly as it is available in nature. We have to do something, but it is aluminosilicate material, but the soil and rocks which is or minerals which is available in natural form is mostly crystalline in nature. They are crystalline structures. Even the clay, soil, or the soil particles or sand particles, quartz particles, they are all crystalline structures. Their atoms are strongly bonded and held in positions by bondings. So, although they are aluminosilicate materials, but they are in crystalline form. So, we cannot use crystalline form of aluminosilicate in the manufacture of geopolymer. So that aluminosilicate source should be glassy form or amorphous phase. So the same aluminum composition will be the same, but it should not be a crystalline form, it should be in amorphous phase. So for synthesis of geopolymer, we require aluminosilicate material in amorphous phase, not in the this crystalline form. If you use crystalline form, there will be less strength development. So where do you get these aluminosilicate materials, which is in amorphous phase or which is in glassy stage, not in crystalline stage? So one more thing, that complete replacement of OPC with geopolymer reduces up to 80% of global carbon dioxide uh, emission. So whatever amount of OPC, production of OPC releases this carbon dioxide, 80% of that carbon dioxide we can reduce by adapting the geopolymer concrete or geopolymer cementing material instead of OPC. Okay. Then coming to that, what is the raw material? Where do you got this raw material from for geopolymer production? So the mostly it is a waste material, industrial byproducts or waste material. So if you have an industrial waste like slag, blast furnace slag, fly ash, rice ash, red mud, municipal solid incineration ash, these are the industrial byproducts. So nowadays we are not telling waste, all are byproducts. We can use them in our construction or some other purpose. Then we have the construction and demolition waste, the construction cement, concrete, brick, this crushed brick, or that you can use also for production of geopolymer. Then agricultural waste, we have the rice ash, sawdust ash, bagasse ash. All this material can be used for or as a mineral resources for the manufacture of geopolymer. And you see that if I come to that, I am telling that blast furnace slag and fly ash. And if I ask, so what is a fly ash? And this fly ash we used to get from the power plants, burning of coal. We got the fly ash. And so what is the fly ash? If the coal is carbon and pulverized coal is burned in the boilers of the thermal power plant, and the residue is fly ash. If a carbon is burnt in the boiler, carbon get oxidized and it becomes carbon dioxide, which is released to the atmosphere. Then what is left? The left out portion we call is a fly ash. But if you see this coal, it is sedimentary rock. And once it gets sedimented, in between there are layers of earthen material left or entrapped during the formation of coal. So once you take the coal block and pulverize it, this earthen material get mixed this one. And once you burn the coal in the boiler, this carbonaceous material get converted, oxidized to carbon dioxide and releases to atmosphere. Only the thing what is left is not nothing but it is only the burnt earth, burnt earth. And I told that earth is nothing but it is a aluminosilicate material. But burnt earth is in glassy phase. It is in amorphous phase, because once a material is heated to a high temperature like 1300 or 1400 degrees centigrade and cooled rapidly, the crystalline structure will not be formed. The atoms will not be arranged in a particular shape or fashion to have a crystallized structure. So it fails to form a crystallized structure. If it is cooled gradually, then a crystalline structure will be formed. So a material, earthen material, which is heated and suddenly cooled, forms a aluminosilicate source for formation of geopolymer, which is in glassy structure. Similar to that, fly ash, the blast furnace slag. It is an iron ore which is put in the furnace, blast furnace. Then we use the limestone, dolomite for to reduce the temperature. And once it melts, this iron, molten iron, is taken from the bottom of the furnace and the top, the flux. It is a mixture of the earthen material and the lime what you add to the during this melting process. So blast furnace slag, it contains the earthen material as well as limestone. So if you analyze the chemical composition of blast furnace slag, it will the aluminum silicate material which we obtain from the earthen materials and the calcium oxide. And if you see the chemical composition, it will be calcium oxide mostly and the aluminum silicate material. And all them are in glass stage because we just, if you dump it, we'll get the blast furnace slag. But if you granulate it, every of all of you might have known the granulation of the blast furnace slag. But only blast furnace slag is not a glassy, it is not a glassy material, it is semi-crystalline material or crystalline material. But during the pouring, we adapt a process called quenching process. The high pressure water jet is spread to this molten slag, which is get fragmented, small pieces are formed, which cools down very fast. So the glassy structure will be formed. The blast furnace slag, which is previously we are pouring the blast furnace slag like this one, which cooled very slowly, there you will not find the glassy structure. But nowadays, what you do, we are manufacturing the granulated blast furnace slag, the same slag, but we spray the water jet, the quenching process. In that process, the huge mass of the slag, it gets fragmented like small pieces of sand-like or silt-like particles, very small particles which get cools very quickly in the atmosphere. So that is a glassy structure, and that glassy slag we use in cement manufacturing process. The manufacture of slag cement, what we call by adding the slag, that is the granulated slag, not the blast furnace slag, what we manufacture long back. That is not useful in the cement manufacturing because they are in crystalline or semi-crystalline stage. That will not add to the pozzolanic effect. It should be in a glassy stage so that it will be reactive and participate in the reaction process. So my point is to tell that we have to use a aluminum silicate resources source material which is in a glassy phase, not in a crystalline phase. And all this material are the we so called the industrial waste, slag, fly ash, rice ash, all these things, red mud. So where there is a rapid cooling, after heating there is a rapid cooling, the glassy structure will be formed, not amorphous structures. So this is the basic raw material. Then there is a alkali activator, and we use sodium hydroxide, potassium hydroxide, sodium silicate, sodium carbonate, sodium calcium carbonate, and the manufacture of geopolymer we can adapt by activating both the alkali activated process and acid activated process. In acid activated process procedure, you use phosphoric acid to, but the research on this acid activated geopolymer is very less. Most of the work is on alkali activated material. Okay. Then if you see that materials, the raw materials which you use for manufacturing of a geopolymer, it is put like this one. We have this Portland cement, the composition. This is the calcium axis, then we have aluminum and silicon axis based on the composition of the material. We have this Portland cement comes here. This is the slag, blast furnace slag. This is the fly ash, and you can see that class C and class F fly ash here based on their calcium oxide composition or other composition. Then we have this red mud, metakaolin, silica fume, limestone, and all these things. All this material we use in the synthesis of the geopolymer, or you can use as a binding material. So then coming to this raw material production, suppose if you see blast furnace slag production, the steel slag, so the top producer is the China. You see this, and India also the second largest producer of crude steel as well as blast furnace slag and steel slag also. These are the production and huge amount of this slag or waste material or what we call the byproduct, which can be effectively used in the production of geopolymer, is generated in India itself, because both fly ash and we are the second largest producer of fly ash and slag, which are the main component in the production of geopolymer. So, the next slide. Okay. And this is also the coal ash generation in our thermal power plants. You see that present generation is 272 million tons of coal ash annually in India. So, what by showing this slides, what I want to tell to you only, we produce the raw materials or industrial waste. What we produce is very much useful for production of our geopolymer cement or geopolymer concrete. So we have the raw material with us. Then the process and technology. So both the fly ash and slag, what you produce from steel industries and thermal power plants, are very much suitable to be used as a precursor material for manufacture of your geopolymer. And we produce a huge amount of these materials. Then coming to, okay, then another material which is the recent research work is going on is the waste glass, use of waste glass in geopolymer production. So we use as a glass parts. In the glass there are different varieties of glass, and this is the soda lime glass which you can use in the manufacture of geopolymer or improving its strength and durability. Particularly the durability aspects of geopolymer can be improved substantially by using the soda lime glass. And this is the glass production, waste glass product generation in different countries, and this is the recycling rate. Still there is a big gap between the production of waste glass or generation of waste glass and its recycling rate. There is a gap, and we can use also waste glass, particularly this soda lime waste glass, in the manufacturing of geopolymer, particularly with some addition of 10 to 15% of waste glass lime, waste glass, so that the durability properties of geopolymer will be enhanced many times. So durability is a major concern also. Then coming to that geopolymer process, ये क्या हो गया है इतना आ रहा है okay, ठीक है. So the process of geopolymerization process is like this one. We have the raw material, and the raw material should be the aluminosilicate material in glassy phase, not in crystalline phase. So aluminosilicate material in glassy phase. Then we have a activator. Either you can have an alkali activator and or acid activator, or acid activated geopolymer or alkali activated geopolymer according to local. But most of the research is on alkali activated geopolymer. So we have a raw material and an activator, and as I told, this activator is mostly sodium hydroxide, potassium hydroxide, silicates of sodium and potassium like this one. Then if you add, there will be dissolution of the raw material, and what this raw material contains is the silica, alumina, oxygen, and all these things. So those elements will get dissolved. We will get silica, alumina, oxygen, hydrogen like this one, and of course we are adding sodium here. Sodium, alkali activated means or sodium or potassium. So what you got by adding these two, the elements will get separated because it is amorphous structure. So it will be easy to detach the elements like silicon, aluminum, oxygen, hydrogen, and sodium available with this. Sodium or potassium or whatever this alkali material we are putting, accordingly we'll get here. So once these dissolved ions are available in aqueous form, then the formation of tetrahedral silicon, alumina, tetrahedral units formation will be there. Then the next step is the nucleation, in which the aluminosilicate oligomers will be formed. that I will tell you what is this one. Then the process of oligomerization. Then there is a release of water here. It is different from that cement hydration. In cement hydration, you need water for hydration process or strengthening process. But here, whatever water you have added, and some water will be released in this process. Then polymerization, then we'll get a geopolymer paste, and once it hardens, we'll get hardened geopolymer. This one will see the one by one step. So this is the silica and alumina tetrahedral unit. We have central silicon and 4 oxygen atoms arranged in a tetrahedral unit. This is the base plane of triangle and another 3 triangles in 3 sides. And similarly, aluminium. So we call it silica and tetrahedral units, alumina tetrahedral units. So this is the basic structure of geopolymer started, the first phase of. First is dissolution, then formation of this type of structure. And this structure is given by Davidovits. So next, this is linked to form a chain-like structure or continuous structure. We have this, depending upon the silica alumina ratio in our aqueous solution. If it is close to 1, we call it a polysialate. If it is 2, we call polysialate siloxo. If it is a silicon to alumina ratio is 3, we call it a polysialate disiloxo. Here a sialate ring like this one. So next you see how it is linked. So if the silica and alumina ratio is 1, you see the structure, there is 1 silicon, 1 aluminum, then OH group is there. And if you see that middle oxygen here, it has a negative charge deficiency here. So that is shared by a potassium ion. No, not oxygen, this aluminum. You see that this is silicon, which is a +4 charges, positive charges, and which is shared by covalent bonds. So each positive charge is shared by a negative charge here. So it is balanced, this silicon. But if you see this aluminum here, it has 3 positive charges shared by 4 units, 1 covalent bond here. So this aluminum is a shortage of is valence here +3, but this shared by 4 negative ions. So it has a shortage of a positive ion. It is a net negative balance, which is balanced by a potassium cation. So that potassium or sodium, it is supplied by the alkali material. So a structure like is formed. And if the silicon to aluminum ratio is 2, this type of structure is formed, what you call sialate siloxane. Yeah. So here, the silicon to aluminum ratio is 2, this structure. And here, silicon to aluminum ratio is 3. We have 3 silicons and 1 aluminum. This structure may be like this one or like this one. And here you see that this aluminum is a net negative, higher negative charges, so which is balanced by a positive cation here, potassium, sodium here. So this is the need for a alkaline cation, positive cation to balance the charge here. So based on the silicon to aluminum ratio, either a structure, this is the basic structure, either this type of structure, or this structure is formed. This is the, so again, this structure is formed. This is the final geopolymer structure. So the difference between here, this is a single structure we have seen with silica aluminum ratio is 1. So in the next stage, what happened? From the OH group, hydrogen is removed. And this oxygen is shared by another silicon here. So like a chain reaction occurs. So now this is a single unit of silica to aluminum ratio 1 is a structure is like this one. But this H group will not be there, OH will not be there. Finally, it will be oxygen. This hydrogen will be removed. So oxygen will be -2, but it will be one charge will be shared by this silicon and one more silicon will be this, and the similar structure will be repeated to this side, this side, this side, this side. So it is a chain-like structure will be there. So once the hydrogen is released here, so it will again combine with the OH group, then the water will be formed. So I told you that during the process of oligomerization to polymerization, water is released. It does not need extra water as it happens in case of this hydration of cement products. Here, some amount of water is released, but we need to add water so that there will be an aqueous solution, so the transfer or movement of the uh, elements from one place to other, so that a bonding will be formed. So water acts as a medium for the transport of the ions or metal and OH oxygen ions like this one. But finally, it releases water in the process and we'll get a 3D structure. So this is the basics about we civil engineers were not that much bothered or interested in how the structure is formed. We, as a civil engineers, were more interested to know the strength, the durability, performance, fresh properties, hardened properties, and like this one, and all these things. So if, as I told, the silica to alumina ratio is 1:1, we'll get tiles, ceramics, and those geopolymer can be used for tiles, ceramics, fire resistance. No, if it is 2:1, cement concrete. So you are our this for the manufacture of geopolymer cement, this ratio of silicon to aluminum should be 2 and slightly above this 2. So we'll get cement concrete and all these things. If it is more, then the properties of cement, what you need require or compared to the OPC will not be there. So you will not be using 2 to 3, and that will be most optimum, I'll tell you. Still higher you can go. But depending upon the silicon aluminum ratio of it should be there. Then we'll have this. How we will produce this one? Okay, the process of production of geopolymer concrete. You have a coarse aggregate, as usual in the production of your OPC or concrete from OPC. We have a coarse aggregate, then we have a fine aggregate like sand, then we have a cement in conventional concrete. But here we have a aluminosilicate material, and this aluminosilicate material should be in amorphous stage. I am just emphasizing that aluminosilicate material should be in amorphous phase. As we got amorphous phase, we'll get volcanic ash, we'll get amorphous phase, we'll get fly ash, we'll get in silica. Silica, actually, this aluminosilicate ratio will be silica to aluminum ratio is unbalanced because it is a silica rich compound, aluminum is not there. But fly ash is one of the most preferred material with aluminosilicate ratio is 2:1. I told that 2:1 silicon to aluminum ratio is better for cement, geopolymer cement. So we have an aluminosilicate precursor. Then we mixed all these three in dry condition by mechanical mixing. Then we add alkali activator. Then we add water, required amount of water to have this consistency and all these things. We add this too. Then we can mold it and allow to you. Yes. Is there any? Okay. So if you have any questions and all these things, we can have a discussion at the end of this presentation. Okay. So adding these things. So what is the problem associated here? But cement, the production of concrete, normal concrete, conventional concrete, we have coarse aggregate, fine aggregate, and cement. And we add water. This alkali or this is not there. But here the problem is that storing this alkali material, liquid alkali material in the construction site is a concern, or it is a drawback in the field manufacturing. So cement, we keep it in the bag, then you add this coarse aggregate, fine aggregate, and water. But here this is to be added in liquid form. And if you add in solid form and water, this formation or strength development will not be that high. And storing, this is a highly corrosive material, and storing liquid corrosive material is a problem. Nowadays, as I told you, that we call two-part geopolymer concrete. That is the solid and a liquid alkali activator we are adding. But nowadays research is then one part geopolymer. This alkali material in solid form is mixed there. And what you need to do in the field is coarse aggregate, fine aggregate, and alkali, this aluminosilicate precursor and alkali material mixed together here. You have to add only water here. So that research is there, but it has to be stored in airtight bags and all these things. But it is in a research stage. One part geopolymer. What I am talking about, this one is the two-part geopolymer. This is one part, solid part, and there is a liquid activator we have to add in the field. That is one of the drawbacks. So coming to the factors influencing geopolymer mechanism, we'll see how good geopolymer can be produced or what are the factors influencing this one. First is the type of aluminosilicate precursor, fineness of the precursor, specific surface area. We measure fineness of the material in terms of specific surface area, type and concentration of alkali activator, what? Okay, molar ratio, silica to aluminum molar ratio, sodium to aluminum ratio, calcium to silicon ratio. That should be a proper ratio or range of ratio, which gives you the best geopolymer. Next is the liquid alkali activator to solid binder ratio, then water content, time of mixing, curing regime. All these things influence the strength and durability of the geopolymer. So if you see this first is the type of aluminosilicate precursor. I told you that this aluminosilicate material should be in glassy form. Then once you add alkali to it, the silicon aluminum they are released from the source material, and again they are rearranged to form a structure like that we have seen. But if you see, this is the second figure, figure 12, shows that the dissolution of silicon aluminum. It is not only the availability of silicon silicon and alumina in the resource material, how much it gets dissolved. Because the bonding stress, silicon and aluminum in the material will be in oxide forms. And if you add alkali, then they will get released. But the bonding between the silicon oxygen and aluminum oxygen is different strength, bonding strength. So different magnitude of silicon and aluminum will be released from the aluminosilicate material. Though it contains aluminosilicate material, all will not be released at same concentration of same molarity of the alkali. And you see, this is the variation of, you see that at around 8 molar concentration of sodium hydroxide, the release of silica and alumina ions will be highest. If you have low concentration of molarity of this alkali, the release of silicon aluminum is less, and if it is more also, it is a release of is also less. So that is an interesting thing here. You may ask, so if you are increasing the strength of alkali, why this dissolution reduces after a optimum? And most of have had this congealing effect. This also we have seen in case of cement hydration. So cement hydration or these hydration products in cement also occurs in a alkaline environment. And we see that if the alkaline environment or pH value of this medium is around 12.4, the strength and durability of the conventional cement is good. If the alkaline environment is very high, again the poor quality cement is concrete is formed. If it is less, it will not be also a poor quality concrete is formed. And the contribution of the process is like this one. So first is the dissolution of silicon aluminum from the source material. Then there is a okay. ये क्या है इसको? ये कुछ नहीं है. ठीक है. फिर what happens here? There is a release of the silica and alumina from the aluminosilicate material with this alkaline environment. And if you increase the am I audible again? Dr. Meena, am I audible?
Uh,
Okay. Yes or no? Whether my slides are visible and I am audible, because in between.
yeah.
Okay. Then it's fine. Okay. So we are here in this visualization process because what happens that if you increase the molarity or concentration of sodium or alkalinity, the dissolution process becomes faster. So the process is that there is a source of aluminosilicate and there is this alkali solution which takes the silicon or separates the silicon and aluminum from that source. And then this separated silicon aluminum, it takes a structure or it is arranged like as we call oligomer, polymer and all these things, then it sets. Then what happens if the concentration of alkali is very high, the dissolution is high. But in the same time, the formation of oligomer, polymer and setting occurs. So in that process, what happens? It is so fast that uh, the polymer which is formed, it sets and coats the source material. Suppose you have a fly ash source material from which you are taking silicon alumina. And if the uh, concentration of alkali is very high, the first release of silicon alumina occurs. But in the same time, the first setting of the polymer also occurs. And this polymer, what will happen? It will set on the source material. So if the polymer sets on the source material, it covers the source material. So it will coat the source material. So now the although there is a source material, it is covered by a polymer coating. So no more source material or silicon, alumina will be released from this one. So what you need is a first release, sustained release for a longer time. If the alkali concentration is very high, so that happens. And this is a term which we use, if you see that, congealing effect. That is the source material is getting coated with this geopolymer form is so fast that all the source material will not be consumed. So it will be covered. So will not you cannot use all the source material for the development of geopolymer. So if the process is very high, alkalinity is very high, this happens. So there is a optimum alkalinity depending upon the source material. And for the source material, what I use here, it is about 8. And most of the research, it is 8, 9, at best it goes to 10, not more than that one. If you use a alkali, high strong alkali, the strength and durability also hampers. Strength hampers and durability also hampers. So this is the aluminosilicate percussor. And then we have this fineness. As you know that this, if you increase the surface, specific surface area, if you grind the material, ultra fine cement or ultrafine material, the reactivity occurs because this reaction is a surface reaction. If the surface area is high, the reaction will be very fast and more silica and alumina participate in the geopolymer production and contributing to the strength. And if you grind the material, you have seen these fly ash particles. Schematically, you have seen that fly ash particles which have spherical particles. Suppose if you grind it, it became the smaller particles and its specific surface area increases. Again, if you grind or pulver this one, it will be very high surface area. And because this release of silica and alumina occurs from the surface only, and so if the surface area increases, the release of silicon and alumina ions also will be very fast, and the geopolymer product will be very strong, and large amount of this material will be produced. So more ionic dissolution takes place from the percussion, enhancing the reactivity of the material. So this is about the fineness. If you increase, that is very common because if you know that to have a high strength of cement, it should be ultra fine cement because the strength to be increased or it is a surface thing. Then the type and concentration of alkali. So normally you use sodium hydroxide, potassium hydroxide, sodium silicate, potassium silicate, and all this thing, a combination of this thing. So use this silicate in conjunction with the alkali material because sometimes we find that the silica to alumina ratio, which should be 2 to 3, is not maintained, is not got from the source material. Whatever this source material like fly ash we are using or slag you are using, if it is not maintained, silica ratio is less. So to supplement that silica, we used sodium silicate. But the release of silica from sodium silicate is easier. The bonding between silicon and oxygen here is very weak. So if you use sodium silicate in conjunction with sodium hydroxide, you will get a lot of silica ions from this one, which will have this optimal value of silicon to aluminum ratio is 2:1. So that will give you better strength. So appropriate alkali concentration. So there is a lot of research, cation diameter and all these things. So, but in nutshell, it depends upon the concentration of this one and type of the alkali and source of this is the secondary source of silicon. If you add sodium silicate, potassium silicate in conjunction with sodium hydroxide, that will be secondary source of silicon to the structure. Then we have this molar ratio. So what I told, this optimal range of silicon aluminum ratio, as I told you, it is 2 to 3. So it is 2 to 3 in the aqueous solution, not in the material. So material, there may be some silicon to aluminum ratio, but how much it dissolved in this aqueous solution. So whatever there in the aqueous solution, that takes part in the formation of geopolymer. So in the aqueous solution, after dissolution, the silicon to aluminum ratio should be in between 2 to 3. So optimal range of sodium to aluminum is 1, and optimal range of calcium to silicon ratio is 1.18 to 2.2. So if this is the ratio is maintained, we will get a better geopolymer and better strength and durability. Then factors influencing this liquid to alkali to solid binder. It is similar to this one. So this liquid to solid ratio is an important parameter that also we determine for our conventional cement. If you have a more water, the structure will be porous. If it is less water, also there will be maybe segregation and all these things. Similarly, here also there is a optimum liquid to solid ratio, which you have to find based on the source material. What is the raw material you are using? What type of alkali you are using? And these characteristics of your mortar and all these things that you have to find out from the lab test. Then water content. Initially, so as I told, the initially available water content is consumed during dissolution stage, and a fraction of same is released during the oligomerization process. As I told that from OH group, it is converted to oxygen and hydrogen is released, and that forms the water. So in this oligomerization process, water is released. So, and water also is responsible for the uh, good consistency and formation of the material. So time of mixing similar to your mixing of cement to in concrete formation, there is optimum time. If the time exceeds that way, there is a segregation, or if the time is very less, there will be not homogeneous mixing of this one. Similarly, also similar thing also here in this mixing time to find the optimum mixing time of raw material. Then the curing regime. So geopolymer can be formed at any temperature, ambient temperature, and all these things. But it is found that initial heat curing is very beneficial for the production of or strength and durability of this thing that we will be discussing. And most of the research paper they told that initial 24 hours, that is 3 days of heat curing. After that, ambient curing, maybe 20 to 30 degree curing will give you good strength. But initially, if the curing temperature is, as I told, that any temperature above the freezing point of water, it can develop the strength, but it is found that initially heat curing is very much beneficial. So then advantages of this geopolymer over this thing, it reduces 80% reduction in carbon emission, higher strength and structural properties, low creep and strength, higher resistance to fire and chemical attacks, low permeability, better encapsulation of metallic ions. Because as I told that most of the materials, raw materials we use are the industrial waste or industrial byproducts, and they contain metallic ions, heavy metals, toxic elements, and all these things. And a geopolymer, this structure, it encapsulates the ions, metallic ions, which is harmful. Otherwise, it will be leached to the surrounding and create environmental impact. So it is a good encapsulation of the ion occurs. So reduces the waste management issue. Several industries highly suitable for the precast industries because it's a very fast setting material. So disadvantage, this field studies. So if you see that research is available in geopolymer, depending upon the method of manufacture, raw material use, then all the parameters which we have discussed earlier, different strength will be there. There is no generalization about the strength, durability, production process, and all these things. Till now, it is not evolved. So lack of uniformity in the research outcome. There are some contradictory research outcomes are also there. Cost higher.
That not audible. Hello. Hello. आ रहा है
There are some disadvantages there, and one of the biggest disadvantages is handling this alkali in the field. And I told that there is a solution to that. There is a one part geopolymer. People are researching on this one. So coming to this, I will just highlight some of the things what we recently do in our institute here. So this is okay. This is what we do. So many research work is there. Geopolymer produced from slag, produced from fly ash, other raw material, aluminosilicate material, or binary geopolymers. So recently we have tried with granulated blast furnace slag with soda lime glass. I told you there is a huge amount of waste glass dumped or thrown. And the soda lime glass, the motive of using the soda lime glass in geopolymer, because geopolymer we require alkali material. We use sodium hydroxide, potassium hydroxide, or silicates as a source of alkaline material. This soda lime glass contains high percentage of sodium hydroxide. And if you use a part of the soda waste glass along with this slag, the consumption of alkali material will be reduced much. This is one of these things. And second thing, what we find, so the production cost will be reduced. I will be using this soda lime glass, so that the consumption of fresh sodium hydroxide or sodium silicate will be reduced. And second thing, that soda lime glass contributes silica. We require more silica than alumina. It is in the ratio of 2 to 3. So it gives silica. Getting silica from soda lime glass is easier than getting the silica from this slag or particularly this bias. So it releases silica. And one more thing, if there is excess silica left, once it is subjected to high temperature exposure, one of our concern is that if our structure is subjected to high temperature or there is a fire in our structure, so concrete disintegrates. But here, if there is a silica left, silica will melt and it will breeze the gaps, and the residual strength will be high than the compared to the conventional cement. This is what benefit we observed by using 10 to 20% of 10 to 20% of slag replaced with soda lime glass. So I will tell some of the select research things what we got here. This is the material. We have the slag, soda lime glass, sodium hydroxide, like this one, the similar fine aggregate. This is the gradation curve for this one. This is the SEM images of slag and GP. GP is for glass powder. Soda lime glass we collected from the dumping yard, and this grind it in the ball mill, in the lab ball mill, and sieved it like this one. And this is this thing, except the image of both glass powder and slag. Both are amorphous. There is no remarkable peaks. There are only two humps there, and this humps here shows that the material is in glass stage or amorphous stage. There is no crystalline structure. And as I told that the material, aluminum silicate material, should be in glassy phase. So that will give you better geopolymer. So both the material what is found from the XRD is highly glassy or amorphous. So this is the composition of slag and GP, and you see that sodium oxide, 11% is there in GP. So this adds, so that reduces the consumption of sodium hydroxide, what you use as a alkaline activator, that the amount of sodium hydroxide can be reduced because this contains sodium oxide here, sodium cations are there. And the release of silica is also more here, and it also contributes silicon ions for geopolymer production. So these are the two advantages by using GP along with fly ash or with slag and all these things. So we have tried with a different GP content, then the sodium hydroxide concentration starting from 2 molar to 10 molar, liquid to liquid alkali activator to solid binder ratio starting from 0.25 to 0.45. And as we have prepared these mortars samples with standard sand and binder ratio of 3:1. So then what you find out these all these things actually time will not permit. I will just tell you the salient feature where the solubility of slag is the basic thing you have to see. The release of silicon and aluminum ions. So first thing you have to go for the solubility, then study the fresh properties like setting period, soundness, then the hardened properties, compressive strength, mineralogical study, and then this is the durability. So in the durability, you have uh, studied this resistance to fire attack. As I told you, if you use soda lime glass, this the residual strength after the exposure to fire will be high because it will retain the strength even though it is exposed to high temperature. That is one of the major things we got here. Then the resistance to freeze thaw wetting drying cycles as similar to what we do for the conventional cement and all these things. This is the wetting drying and freeze thaw cycles, water slacking, then resistance to acid attack, that is the chemical acid, alkali silica reaction, and last is these are the durability studies we have made on this slag GP binary geopolymer. So this is the dissolution, as I told you, with different release of aluminum and silicon from slag and GP. These are the things with the different molar concentration of alkali. So this is the one of the thing is the quick setting of this geopolymer best. So normally OPC you should have an initial setting time of 30 and final setting time of 10 hours. But if you find in geopolymer, the setting time is too less. So sometimes we use borax to increase the setting time because it is a very quick setting material. So we modify this here by adding some compounds to increase the setting periods. But it is observed that it is too less here. It is only instead of 600 hours, it is 10 hours final setting. We got it all this thing and less than this one. That can be also here. This is the workability to study this workability. We have 2 molar alkaline solution. G0 means your glass powder 0. We have 20% glass, 30, 40, like this one. This glass slag is replaced by glass, and here we have this molarity 2 molar, 6 molar, and 6 molar. As you increase the molarity, the workability reduces, and again, if you increase the glass content, this workability also reduces. That happens the effect of this angular glass particles on the workability of the and as the alkali solution is viscous in nature. As the molarity increases, the viscosity increases, and the flow, this workability also reduces. This is very common thing. Then we have the soundness of this one. Soundness, as you determine, this is with the different molarities and with glass content. And as per this IS 4031, the soundness should be less than 10 mm, but we got a maximum of 4 mm soundness. So it is within the permissible limits are there. Then drying shrinkage, again, if you increase the glass content, the drying shrinkage value reduces at the different curing days starting from the 7 to 28 days. Okay, so it is has less shrinkage value compared to the OPC, this slag. This highlights the use of glass powder, replacing slag, a part of slag by glass, soda lime glass. What is the benefits you are getting out of this thing? And then the compressive strength. with different molarities and different glass content things. But as you see that here, you can notice that if you replace the slag by glass powder, the strength reduces continuously. This happens with normal curing. Normal curing means what I tell that an ambient condition in between 20 to 30. So because the release of bonding will be strong, release of silicon will be less, and a particular slag will have lot of calcium component. So in addition, in the geopolymeric product, if you use slag, we will have hydration products because there are calcium, so we'll get calcium silicate hydrate, calcium aluminate hydrate in addition to the geopolymeric product. But if you replace the slag with glass powder, we will sacrificing these hydration products like what do you call calcium hydrate, calcium aluminate silicate, and calcium as we got in the cement, that will be sacrificing. But with high temperature, the strength increases. So this gives you the normal temperature at ambient 30 degree. Everywhere they are still get less strength if you increase the glass content. And one more thing that we will get this solid to ratio, liquid to solid ratio at 0.35, we got the maximum strength. This is the dry side of the optimum. This is the wet side of the optimum. For this particular case, we got this liquid to solid ratio as 0.35 as the optimum value, give a higher strength. So based on the 20 days compressive strength result, the optimum sodium hydroxide concentration is observed to 6 molar and liquid to solid ratio is 0.35. So, but if you don't use this glass powder, this optimum molarity of alkaline will be 8. So you are saving 2 molar sodium hydroxide material if you use the glass powder because glass has a sodium in it. So this is about the ambient curing 30 days, and this is the strength gain with the curing period of 90 days. Yes. I have only 20 minutes, okay. This is the micro ACM image, and where you can see that if you cure at very low temperature, minus 15, 0, and all these things, lot of void space are there. This geopolymer paste is not formed, and this hardening, it has not set, and strength will be obviously, it will be less. So then this is the at high temperature curing at these are the graphs with different initial curing temperature starting from 30, 45, 60, and 90 degrees Celsius. And as you see that this temperature increases, the strength gain with time also increased, and the final strength will also be high. So what it tells is that we require although it is told that at a temperature say above freezing point, it will harden, but the optimum temperature or the most optimum value will get at a temperature of 45 to 60 initial high temperature. And based on the study, you will see that so the specimen should be cured at 60 degree for 3 days, followed by normal curing. So initial high temperature curing favors the high strength gain and high ultimate strength. And here, then one more thing we have investigated about the normally in concrete what you do is that curing is done under water. If you put the specimens in water, then similarly after 1 day, if you demold these samples cubes, then we try to put water at different temperature, and the temperatures of water is 30 and 60 degree we have maintained. But we put this samples in normal water, tap water, then again alkaline water, then saline water, and like this one. So what I find, if you put our samples in normal water, tap water, and we have sodium hydroxide in it, and there is a escape of sodium hydroxide from the sample to the water. That means because the after 1 day, if you put the samples in this one, all the sodium hydroxide the activator what we have added is not used for this production of geopolymer. So some of them is leached out, so the strength reduces. So if you have a geopolymer sample and put in the normal water for curing, there will be a reduction in strength. So instead of this one, if you have alkaline water, the same thing, the strength reduction will not be there. And as the temperature increases, also the strength increases. So if you curing is to be done in by putting in water, like other conventional thing, it should be a it should be alkaline water, so that the leaching will not be there, balancing will be there, concentration of the alkaline material outside and inside should be there. So the loss of sodium hydroxide will not be there. Then we also tried, as usual, with autoclave curing, as we do for this cement. So we got a strength of about 75.7273 MPa in 1 hour and 2 hour at 1 megapascal this pressure. We got a 72 MPa of strength, and similar to your cement also. If you go for the cement, the accelerated curing or autoclave curing, the strength in 1 2 hours or 4 hours will get a very high strength. Or similar also we got this thing. So we also conducted the curing in these other macro events also, uniform curing. So shrinkage cracks will not be there, uneven curing is not there, these slides are not there. So you see that the solid materials are formed once the autoclave curing we adapted. And then, so this is something, the initial heat curing of 60 degree for 72. After that, there is a normal curing. Then also we got a very high strength, as high as 50 MPa. All these things are there. This is the XRD to find out the what is there, the formation of materials in this one. So what you got is, if you have this, we have the geopolymeric products will be there, hydration products will be there, and hybrid products will be there. So calcium, sodium based products will be there, calcium based products will be there, and sodium based products will be there, depending upon the availability of sodium calcium ratio. These are the SCM images. So then this is what I want to highlight. DC has a fire attack. We studied the durability against the fire attack, wetting, drying, and freezing drying cycles, water slaking, acidic attack, alkali silica reaction, and all these things. And all these things we have done on a sample specimens prepared at 6 molar sodium hydroxide concentration at liquid to solid ratio of 0.35 and cured for 60 days. Initial curing at 60 degrees centigrade for 72 hours, and after that at 30 degrees for rest 25 days. So total is 28 days curing, but the initial heat curing at 60 degrees for 3 days and the rest 25 days 30 degrees. And the composition of the sample is 6 molar sodium hydroxide and 0.3 liquid to solid ratio. All these tests we have conducted. So this is the fire attack. So this is the mass variation, mass loss of, this is the normal Portland cement mortar. You see there is a lot of loss in mass after exposed to high temperature. This high temperature is from normal temperature to, we have increased at a rate of 5 degree per minute to this 200, 400 or 600, 800 or up to 1000. Then we kept at 1 hour with this elevated temperature, then gradually you have reduced. The procedure we have adopted is like this one. The samples, cured samples, 28 days cured samples. So then from the normal temperature, around 30 degree Celsius ambient temperature, it is gradually raised at 5 degrees centigrade per minute till it reaches this temperature, 200, 400, 600, like this one. Once it is reached, then the samples are stored or subjected to high temperature exposure for 1 hour. Then we have gradually reduced the temperature till it comes to the ambient temperature or room temperature. Then we find out how much mass loss is there or what is the residual strength and all these things. And you can see that if it is a conventional Portland cement mortar, there is a mass loss is about 9%, but here it is 1 to 2% mass loss. Huge mass loss is there, and the corresponding residual strength you see this is for 1000 degree. There is a almost the strength has reduced. Much strength reduction is there. Maybe from 45 MPa to around 5 MPa. That much of loss of strength occurred once it is subjected to 1000 degree centigrade heat exposure. But here it has retained almost 20 MPa. All the materials having the glass content, they have retained the strength, but geopolymer concrete and particularly G10 having 10% and 20% glass powder shows the highest retention of the strength under high temperature exposure. This is one of the better finding we got in comparison to our Portland cement. This is the structure after exposure. This is the disintegrated structure, and is that intact gels have their hydrogen products, strong products are there. It is not disintegrated, though it is subjected to very temperature of 1000 degrees Celsius for 1 hour. So these are the structure retained. So this told that this geopolymer is very good in resisting high temperature exposures. Then again, the similar thing, the wetting, drying, and freezing curing cycles. This is the number of cycles. It is exposed to total 12 cycles of wetting, drying, and freezing drying. And after 3 cycles, 6 cycles, 9, and 12 cycles of exposure, we determine what is the mass loss and this one residual strength also we have measured. And you see that this is for this conventional cement mortar. There is a continuous mass loss with exposure cycles, whether it is wetting drying or freezing drying. But you see that this one is for geopolymer mortar. So after it gets stabilized, after a mass loss is about 1.2% mass loss, it gets stabilized. But here it continues for longer cycles of heating drying and freezing drying. This is again the resistance wetting now. This is for the residual compressive strength. Similar strength, similar thing also you observe. The geopolymer mortars, they are strong against good durable material compared to cement, against high temperature exposure, wetting, drying, freezing, thawing cycles, less mass loss, as well as the retention of strength is also very good. This is this conventional select durability test, what you do for the aggregates and all these things. The similar results is also there. G10. G10 contributes better durability compared to the other geopolymer concrete or the geopolymer mortar. We have not shown this concrete here. Geopolymer mortar is much resistant to all weathering actions we have studied compared to the conventional cement and all these things. Okay, feed resistance to acid attack. There is a lot of mass loss you see, and this is subjected to 5% sulfuric acid solution. So there is with a duration of 360 day, 1 year, we put in acidic solution of 5% sulfuric acid, and there is a continuous mass loss in this Portland cement mortar. But geopolymer, there is a less mass loss. Here the mass loss is as high as 60% in Portland cement mortar, but here mass loss is around 25 to 20 to 25%. And if you have this better, it is only 15 or 12 or 15. Again, similar trend is also there in the residual compressive strength. So geopolymer, what to tell that geopolymer are more durable to all type of mechanical and chemical weathering process or elements compared to the cement. You see, these are the samples after the exposure to acid. This is the Portland cement mortar, you see almost all the cementous material has eaten away. Only these sand particles, quartz particles are there, lot of voids are there. But here there are some still some products are there, binding materials are there, so which retain the strength. This shows you visually how this on acidic environment, how there is a reduction of mass as well as the strength in ordinary Portland cement mortar and this geopolymer mortar. Similar to alkali silica reaction, here also geopolymer concrete and all these things, all are below these things. This is here these are within the limits specified in ASTM-C 120, but here it is a slightly higher alkali silica reaction expansion compared to Portland cement. This is just a opposite behavior we have seen here, but it is much within the limit here. It is 0.05 less than 0.05, but the limit as per ASTM is 0.1 alkali silica reaction ASR. Like this, we have seen this maybe the So this energy and peak carbon dioxide release. You see that geopolymer, this is this thing, and energy consumption is much higher in this production of OPC, slag cement, and all these things. But here we have a very less energy consumption as well as carbon dioxide consumption release is much reduced, and overall you will be using sustainable material, waste material. And as I told you, repeat that the durability and strength and durability properties of geopolymer mortar and concrete is much higher than the conventional thing. Only that how to manufacture this thing in the field, how to do this thing, because we will be handling a highly alkaline material in the field. And one more problem associated with that, if there is a unreacted alkali, excess alkali you have added in the field, that will lead to the surrounding ground and water bodies. These are the two major problems associated with this one. And one of the problem is research is there that one part geopolymer, which will solve this handling the alkaline material, storing the alkaline solution in the field. But that is yet to come to the field. I think this is the quickly I have these are the few things we have there. So what I told last thing, this is the part which I have seen. I have told you is the recently one of my PhD student did using glass powder, partial substitution of slag by glass powder. So that time allotted to me, I think I'm very fast to complete. I am 5 minutes excess than my allotted time. If there are a few queries, or if you have a queries, uh, you may take my email from your coordinator, Professor Meena. And if you have a specific queries about this geopolymer, because I am not, as I told you, I am a geotechnical person, but my students, they work on geopolymer because this research started with Professor Minna. She is my first student. She liked to work on geopolymer and we started. I had some training in University of Liverpool on the use of waste materials in civil construction. So that is also additional benefit I got in this area. But now my students are working both in the geotechnical areas as well as in geopolymer, particularly its application to soil engineering, which I have not shown in this slide because here you told that, sir, you limit your presentation only to cement mortar and process only. So thank you. Is there any
Thank
query,
you,
one or
sir.
two? Okay,
From
next speaker
audience, any
is
question
online.
you may ask?
One or two questions you can, then if you have a very specific things, you can contact me on my email and all these things. So Once again, I will be thankful to the organizer giving me
And participant is
Sir, good evening, sir.
good evening.
Thank you very much for sparing your valuable time and giving a very, very informative session for us.
Okay, thanks. Because I am very fast in telling all these things. Okay, what
Sir, my question was
about
even I was
little knowledge collected from my students, research students. Okay.
yes, sir.
Yes, your voice. Yeah. Once
My
again, can you
question was
repeat?
even I was working with geopolymer concrete.
Okay.
Now the activators which are available in the market, sir, NaOH, KOH, which you are telling.
Mhm.
But the papers which we are reading, this NaOH, KOH, all activators are been applicable only to use with the fly ash.
No, no. Fly ash, both fly ash and slag you can use. Slag, we have calcium component is there, but if you add sodium or potassium based, we will get geopolymer products as well as hydration products. Calcium will give you calcium aluminate hydrate and all these things. What you get in normal cement, in addition to that, you will get. If you use slag, there is a calcium, but that
Sir,
will not be
we don't
sufficient.
use slag, and if we use some other like byproduct from like steel slag or bottom ash, so for that one, will this activator
Okay.
work?
So, okay. So I am talking about this bottom mass, fly ash, red mud, and all these things. So one major focus it should be in amorphous phase. So and most amorphous phase will be the fly ash. Bottom ash and pond ash, it loses its polygenicity. On keeping the calcium, whatever little bit calcium is there, our fly ash is a class A fly ash. But if it is stored, this one, whatever little bit of calcium oxide is there, it will be converted hydroxide and carbonate. That cannot be used in our things. And this bottom ash particles is much larger than the fly ash. And as the specific surface area very high, the particles are fine, it will be cooled very rapidly, and the amorphous structure will be formed. Like bottom ash particles is a little bit not much larger than the fly ash particles. So the amorphous nature or glassy nature will be more in fly ash, not in bottom ash. Bottom ash you can use, but you will not, some it will be semi-crystalline, or some particles will be crystalline, some will be amorphous, some will be semi-crystalline. So we will not get readily the silicon aluminum from the bottom ash. So moreover, bottom mass can be used as a replacement of sand and all this thing, because it's a particle size distribution or gradation is similar to sand. But if you are using fly ash, will be much better than the using bottom mass.
Okay, okay. Thank you. Sir, I just request you, please, can you share this PPT with ma'am so that she'll share with us? If you don't have any.
Yeah.
So I will take the
I
permission
will
now.
collect and I
I
will
will talk to
share
the madam.
all the PPTs.
Yes, ma'am. Yes, ma'am. Thank you very much.
Because frankly speaking, it is not my PPT. 2-3 days back, I told my PhD scholar, you prepare a PPT, because my student requested me to give 1.5 hour presentation. So I'll be sharing. So I'll take 1 or 2 days and I'll share it with Professor Meena, and we will share it with you. Okay?
Yes, sir.
Because all these things, what I told you, this is by the this recent PhD scholar. His works has already been published. He has published 7 papers out of this work. I am just telling a little bit of this one, and all these published papers are there, journal papers are there. So no way of sharing this thing. So I can share it, not a matter. I will send it to Professor Meena, who will share it. Okay.
Yes, sir.
So
Yes,
you
sir.
are from which organization, sir?
Sir, I am from Bajaj Institute of Technology, Wardha, Maharashtra.
Okay, okay. Thank you. Thank you, Professor Meena. Have a
So
nice
thank you
day.
very
We'll
much, sir,
continue.
for your good information to the participant. It will benefit for all of us. Thank you, sir.
So you just started this thing, huh? I am a geotechnical people, but you started with a concrete and cement with research from yours. Thank you and good night.
Good night, sir.
Thank you. Okay.
Thank you, sir. Thank you, sir. Ratus, are you there? Please introduce the next speaker.
Yeah. Yes, ma'am.
Introduce to sir. Good evening, sir.
Hello,
Yes, sir.
Good evening, sir.
good evening. Am I audible to everyone?
Yes, sir. You are audible.
Yes, sir. Yes.
Okay.
Yes, sir. Good evening, sir.
Good evening, very nice.
Sir, engineer Kapil Chandoy, sir, is at present AVP Civil at Hira Godavari Power and Ispat. He did his MTech in structural engineering and MTech and having 31 years of work experience in steel and power industries. His expertise includes civil engineering related to steel and power, project planning, execution, structural audit, and rehabilitation. And he is also specialized in supporting structures such as railway siding, building, road, and bridges. Now I request to Honorable Engineer Kapil Chandoy, sir, for the address to the gathering. Thank you, sir.
Good evening, everyone.
Good evening, sir.
Good evening, sir.
First of all, very warm thanks to Ma'am Govardhan sir and all of the team of NIT for giving an opportunity to share valuable knowledge with everyone. I was just hearing the session and I think it was much more valuable. Professor sir has explained the use of polymers, microfibers very nicely and up to a very deep depth. That was a nice presentation. I'm not a professor for it. I cannot present up to that limits, but I'll try my best to share the things with everybody. First of all, I would like to introduce myself. I belong to Godavari Power and Ispat Limited, a steel company which is dealing with different kind of steel products, starting from mining to rolling mills and all those things. So let me introduce a small video so that you will be very clear that what kind of business we are doing and what kind of things we are doing. Am I clearly audible to everybody?
Yes, sir. You are audible.
Is the video very clear? Ma'am, is the video very clear?
Yes, sir.
Okay. So this is our company. It's Hira Group of Industries, and we belong to Godavari Power and Ispat Limited. It's an integrated steel plant. We are working here. My role in this company is as an associated vice president civil, and we are taking care of entire construction activities all around Godavari, around Raipur, Kanker, Dhamtari, and adjoining villages. This is our admin office. This is the place which we are.
Sir, your slides are not visible. Only first slide is visible.
I am playing a video. Is it visible or not?
Sir, it is
No.
not work. Means hold only in pause.
Okay, let me start it again. Now is it clear?
Yes, sir.
Ma'am, is now the video clear?
Yes, sir. It is clear.
Yes, sir.
This is the mines where we do mining activities. From these two mines, first one is from Aridongri and second one is from Boria. And in forthcoming slides, I will be showing up the process, how it is being handled. These are all circuits, how the product is being segregated, sized, screened, and again it is come up being whatever slag, whatever the byproducts you are getting in this, it's an outcome of this process. This is our plant premises. A small temple is also there. These are areas which we are developing. This is the first division, that is pellet plant. Pellet plant produces green steel. It's a pollution-free plant. You produce pellet here, which is commonly directly from the iron ore fines. Whatever fines is being generated, we develop pellet here. This is the entire overall pictorial view of pellet plant. This is the balling mill in which the balls are being prepared. Here the mixed material is being poured and balls are being prepared. This is a travel crate where entire balls are being generated to give it a proper shape. This is the kiln where at a temperature of 1400 degrees centigrade, the balls coming from travel crate are roasted out. This is the cooler where you get the material. This is the kind of material what you are getting it. Now coming to the sponge iron plant. This is a sponge iron plant. Next is power plant. See, this is the sponge iron division. Sponge iron is done by direct reduction process in which Fe2O3 is converted to Fe and O3 is taken out by the help of carbon dioxide reduction. In this process, we feed iron ore, dolerite and coal. In the result, we get pure iron balls. This is the power plant which is feeding up the power charges to everybody. Safety is our first most concern. These are the cooling towers which keep on the system running. This is the electrostatic precipitator from which we, after processing it, we release the oxygen, we release the gases to the chimney. So this is a very small view of our entire plant. This is phase 2. Now I just want to hold it. See, this is ESP, this is ABC DSC building, this is kiln portion. These are all the cooler which is coming up after heating. This section is being treated up, and this is the final discharge where you get the material out. These are all supporting infrastructure. This is the pellet plant output. This is our stock where material is being stored. Now coming to the ferroalloys division, we produce 16,500 tons of silicomanganese, which requires manganese, iron and coal. We are having a steel melting shop where we produced 4 lakh tons of billets. These are the furnaces. This thing I'll explain you in next slides and more in depth. What kind of material, what kind of slag we get. Everybody is talking about the slag, but what that slag is and how we are getting it. This is the process. Next is we are having a rolling mill of 4 lakh tons per annum capacity. This is how the rolling wheel comes up with preparing HB wires. Billets are turned into wires, and these wires further you go with binding wire, nails, and all those activities which is there. This is how they are produced. This is the cooling bed, and now it is on the final edge of packing. This is how things are being packed. This is the wire drawing where HB wire is being brought here and it is being drawn into smaller sections. Here you prepare different gauges of wires are being prepared for different purposes. It can start from binding wire to annealing wires, everything. Whatever gauge you require, it is being drawn here only. These are the small bundles which is being available and ready to pack, ready to dispatch. This is our railway siding. From the finally the material is being dispatched to other states, other countries, and this is the point where we receive the raw materials. This is the entire process and entire business scenario what we are doing here. This is the final picture of Godavari. Now coming back to the topic,
Sir, it is not audible.
hello.
Sir, yes, sir, you are not audible.
I think due to some network problem, it is not clear. Now, is it audible?
Yes, sir, it is audible. Your slide is also not visible. So you have disconnected maybe.
Okay. Acha, what about that video I have played? It is being visible or not?
Yeah, that one is okay. Within a few seconds, it was not visible.
Okay. Now coming back to the main slides.
Yeah, now it is okay. Okay, sir.
So the topic provided to me is use of sustainable byproducts for construction of road and buildings. This is the main product, and the process in which we will forward in this session would be an introduction, whatever the flow charts we do have, a brief knowledge about the materials, what are the steel slags, flow chart for steel slags, and along with some view. And next part is beneficiation, trailing, fly ash, what we are using, the standard and guidelines which is available with us, and Godavari's green initiatives and future projects. This is what the roadmap for this session is. Starting up with a brief introduction. Now, the construction industry in India has seen a rapid growth over the past few decades to keep up with the demand of infrastructure while promoting sustainability. There has been a growing interest in utilizing industrial byproducts. Nowadays, natural products are not available, so you have to go with byproducts only. These materials help reduce the environmental impact on road construction, conserve natural resources, and promote a circular economy. The steel industry, which generates significant amount of byproducts in the form of a steel slag, fly ash, beneficiation tailing, offers a visible solution for sustainable construction practices. Now, this is the process diagram in which I have tried to show how and where the byproducts are generating. This is the, in first part, this is the mines from where the iron ore has been digged out and brought to the plant. Now it has come up to the plant. There are three units. First is pellet plant, second is DRI, third is blast furnace. Pellet plant produces pellet. It gives the pellet to the DRI. DRI is a sponge iron plant, and sponge iron is again shifted to form the billets or a steel plant. And in this process, you require ferroalloys, you require oxygen. For pellet plant, you need iron ore, nitrogen, and for heating this pellet plant, you need gasifier, coal gasifiers. And to run the entire system, you need power plant, or you have to come up with solar plants. So we do have both. We do have 98 megawatt of power plant and 70 megawatt of solar plant. Now, after generating electricity, it also provides to the HB wire, because billets you cannot store. So for billets, you come up with wire drawing, you come up with rolling. All these are the final products which you are getting. Now, what are the byproducts and where we are getting it? First is the steel slag, a byproduct of a steel production used as a replacement of a natural aggregates in road construction. Second is fly ash, a byproduct for coal combination used in concrete and cement production of road construction. Construction demolition of carbon waste, recycled material from demolished buildings used in bases and sub-bases layers, recycled asphalt pavement, reclaimed asphalt from old roads, reused in new asphalt, plastic waste, and second one is blast furnace slag waste. These are the waste which we are using in construction industry. Now coming to the steel slag. What is steel slag? How it is produced and where it is used? Before coming to this tech, I would definitely be willing to share some good slides so that you can be very clear that from where it is coming and how it is using. See, this is the furnace. Ma'am, is it visible? Ma'am, is it visible?
Yes, sir, it is visible, but you make it full screen.
These are the furnaces where we burn up the...
Sir, it is not full screen.
See, this is the furnace where we melt the things.
Sorry, maybe it is not visible.
It is not getting visible.
No, sir. But is faculty member, is it visible?
Not visible.
Okay. Sir,
Okay.
maybe you
Okay, let
open
me
it.
try.
Slides is not visible.
Okay, let me try it again. Is it visible?
Yes, sir, it is visible. Now it is visible.
See, this is the furnace where metals are being melted, and this man is bringing the top dust particles and slag outside the pit by help of this spoon. This is the material which comes out. This is the actual slag which is being transported to slag crusher, which I'll show you in next slide. See how things are being drawn out. This is the furnace. They are pouring the fresh material from this end, and slag has been dragged out from pits to this portion. There is a bucket there, and this metal is taken to a yard. It is further broken down into small particles, and with the help of a slag crusher, this is a grizzlery where we feed 150 mm to 200 mm size grizzly here. Below this is a magnetic separator, a crusher, and high gloss magnetic separator is here. See, this is the slag crusher. Actually, this is the real-time pictures which I am playing for you. This is a combination of building. It is containing slag crusher, screens, and magnetic separators. This is the product where it is coming out. This is where the product is coming up. See, this is grade 1. Here the lies a magnetic separator here. You get two kind of products here, mag and non-mag. The slag which we are using is a non-magnetic material. It is containing very less percentage of iron. See, there are two categories. First one is here in this hopper. Second one is here in the ground. This is the slag which we are using. This is the slag. Here it is. Now, any question up till this point? Any question up till this point?
Faculty may ask any question.
Up till this point, is it clear what kind of slag we are generating and how it is being generated?
Sir, I have a question one. That
Yes, please.
sir, how much Fe is there? That one from PSP plant, one madam has came and she told that more iron are content are there in steel slug. So
in iron content of steel slag, it's around 5%, which is not recoverable.
okay.
If
So
it
it
was,
is
if we feel that it's recoverable, then definitely we would be trying to recover it. See, now I would explain to you in much better thing. We can go for this one. See, this is the process. This is, ma'am, am I clear? Is my video audible?
No,
It
Sir,
sir.
is
video is not
audible
visible,
but
sir.
not.
Not visible. Okay. Let me share it first. See, this is the process how you generate slag, right? Here you feed the
The
material
video
into
is not
furnace.
visible, sir.
Furnace starts burning. The metal is discharged.
Sir, excuse me,
This is
sir.
the pure material you are getting. And in this process, slag is generated, right?
Sir, video is not visible.
Video is not visible.
Yes,
Yes, sir.
only music is coming.
Okay. Now is it there clear?
No, sir. Yes, now it is visible, sir.
Is it there now clear?
Yeah, sir, it is
Yes, sir.
clear. Yeah.
This is the furnace portion. Once you feed the metal into it, you get the results. In this process, slag is generated. Slag is simply the top up portion which is rejected. It contains 10 to 15% in raw form. See, this is what you are going. You are using this furnace into a cone cast, and from cone cast you are developing your steel. Now billet is going to come. This is the billets. Now from billets it has been stored in one place. Now we are feeding it into a rolling mill and you get HB wire here. This is the HB wire which is coming. I've shown the real time video. This is the animated part of it. This is how bundles are being prepared and again dispatched. See. So this is the steel slag which I have shown you in real time as well as for the pictorial view. Now this is how the flow chart of slag is. See, I've given you a brief example how the material is being feed. This is the crusher which is crushing of the material in say size of 20 mm to 10 mm or minus 10 mm is also coming. Again, you come up this with a screen. Below screen, there are two magnetic separators. In first part, you get out one material. Second, high gloss magnet. Again, you circle it and you get a the high gloss magneted part here. It is coming here to the belt and you take it. This is the slag portion. This is the waste which is coming up. The size is from 10 mm to minus 10 mm. This is the slide size which you are getting. Say, now this is the pictorial view. From furnaces, you draw your slag. Slag comes out. It is transported to a slag crusher. This is the grade which you are getting. This is the final material you are getting in part A. This is part B. And the third one is part C. This is the C part. This is what the slag actually is. This material you are getting and exporting it for your regular uses. See, this is the C part. This is the slag which is actually used in road construction. This is a very good replacement of sand. It can be used as an artificial sand also. I think some test has been done with the help of NIT also. They have replaced up to 60 to 70% of slag. This is the slag. Now coming to the theory part. In 2024, global crude steel production related with approximately 1.95 billion metric tons, with which they increase the quantity of byproducts generated. For example, in 2024 alone, India has produced an approximately 144.3 million tons of crude steel, and around 19 million tons of steel slag was generated. Where do we apply for it? We are used in road construction. The waste metal is very good for it. We can go for it. We can in building construction. It can be used in the form of an aggregate. It's the properties are high density and a good binding properties. Next is how to utilize the byproducts in construction appliances. It reduces the waste reduction. Plants is generating waste. They don't need this material, but this is a very good byproduct which can be used in landfill spaces. This will further give a resource conservation, such as for road construction, muram and other materials are rarely available. Everybody you cannot get it. In some parts of India, even sand is a trouble for everybody. But we can go with this artificial sand, and it is having an environmental impact. It is having economic benefit also. So you can use this material. Up to slag, I think it's clear. Or anybody wants to have a question, I can take it. Or I should proceed. Ma'am? Hello?
Sir,
I think nobody is interacting.
they will interact, sir.
Okay, no problem. So let's move ahead. This is the second part, second product which we are getting in steel plants, that is fly ash. As everybody knows, fly ash comes from power plants. It is basically after burning pulverized coal in power plant, it is rich in silica, alumina and other relative compounds, making it a valuable product for construction appliances. Nowadays, fly ash is a very common material available in steel manufacturing. We can go for fly ash bricks as well as in cement manufacturing. Now, fly ash is no more a waste material. It is a raw material for cement plant. Most of the cement plant easily buy it and they use it. See, this is the how the cement fly ash comes. These are the silos where we collect, and after waste reduction, this comes into this process. Let me share a small power plant video for you. I think that picture is not available. So we can go with this third part, that is beneficiation tailing. This is a new product which is, I think, not available with steel plants of integrated in nature. But this is available in abundance and it comes from the pellet plant.
Sir, video is not visible, only slide is visible.
Done. I'm trying to it. I have to close this sharing and reload it. Then only it will be available. This is the pellet plant. This is the stacker reclaimer, which has been metal has been stored from direct from
Sir,
mines.
not opened. Double click.
Now it's clear.
No, video is not opened, only that page is came.
Okay. Let me play it again. Is it clear now?
No, sir.
Okay. क्या हो रहा है?
Sir, आप share the screen, then maybe it is coming. Maybe you have choose that window. Yeah, now
Is it?
coming. Yeah, visible, sir.
See, this is the pellet part which is coming from mines. You are getting it iron here. Iron ore fines are being stacked out with the help of a stacker reclaimer. This is the stacker reclaimer. Once you stack it and again you reclaim it. It goes to the ball mills where you crush different sizes, different combination of materials and feed it. This is the ball mill where you pour the material and granulate that material into highly fine materials. Again from ball mill, you pump it to a thickener where it get condensed and the entire metals burns in a slurry form. With the press of a pressure filter, you again recover the fine particles into a dense particles. With the help of this ball mill, you size it. Again in the skill, you burn it, and the final product you get it in a cooler point. Here you get the product. This is the entire process of a pellet plant, and at this point this is the original ball mill where you get the products. See.
Sir, again double click, not visible.
Is it clear, ma'am?
No, sir, not visible.
Okay. Now is it clear? Ma'am, is it clear now?
No, sir. Sir, not visible.
Slides
Earlier
are
it
visible?
is no, sir. Earlier video also came, but now it is not visible.
Okay. Let me try once more. Is it visible now? Ma'am, is it visible?
No, sir, no.
Sir, better you share your entire screen, then it will be able to visible, sir.
I think so.
Is to be shared.
It is taking.
A
Sir,
screen you have
yeah.
to share. Only it is showing various.
Now, main slide is available or not?
Yes, sir, it is visible now.
So this is what the ball mill is. eh? And from pellet plant, from this ball mill, you get two products. One is finished products, another is byproduct. This is the beneficiation tailing which you get it from this ball mill only. Once coming out from this point, you load it onto trucks, and this kind of material you get finally. This is red color powder which is available. It contains iron particles of say 1 or 2%. Maximum silica is there, and mud is maximum part. So, material is being segregated here only, and this material is now in major use for in road construction, building constructions. You can go for it as a fine aggregate parts. Even brakes, paver blocks are being now manufactured from this tailing material. This is abundant in a very huge quantity, and disposal is also a problem for everybody. So these are the uses what you can get from this tailing material. Now these are the guidelines which government has set for transport department. Higher more guidelines are available for sustainability, quality, environment impact, and going for a pilot project. We go with the research collaborations with NITs, RITs, all those things, and compliance is major adherence for it. These are the chemical properties which minimum requires for fly ash as well as other materials. For fly ash, these are the properties for physical. The granule size should be 10 to 60 mm. Crushing strength is 40 MPa. These are all metal for slag. For fly ash, chemical composition is there. For filling material, design specifications are there. Say, for fly ash to be used in concrete, it should be 35% of the weight of cementitious product, and it's achievable. Minimum strength, you are getting 30 newtons per mm square in 28 days. Workability, it's really high. In cement, you can use fly ash. In bricks, you are using fly ash. And these are all the green initiatives which we are taking. We are manufacturing bricks, we are manufacturing paver blocks, we are manufacturing road materials as well as cementitious material. We are using it in different kind of prospects. The use of steel industrial byproducts in construction has given up a big potential in revolution of industries, making it to be a more sustainable and a eco-friendly. So, and above all, there are some other materials which you can use in your building construction, such as bamboo, hemp crates, recycled steel, reclaimed woods, rammed earth, cork, recycled glass. All these are materials available all around us and we can use for it. So, thanks a lot to everybody. Any questions would you like to ask? I'm there to answer you all. I think interaction is very poor.
Dear faculty member, sir is from field. We should ask the question. We people are theoretical, but sir is in practical. So we can ask. We are working in fly ash also, slag also, GGBFS.
You're
So,
providing us the technical guidelines also.
so we can ask. We can interact
Yes,
with him.
even that slag trials has been done in NIT only, and I think one of your student has replaced it up to 60 or 70. Murmu madam
Yes,
has
sir.
also done it also.
Yes, sir. Yes, sir.
Yes, it's
Hello,
there.
sir.
Yes, sir.
Hello, sir.
Yes, sir.
Sir, actually in India, fly ash is maximum 35%. They say that by, mass of cement they replace, no? So I think some of the, foreign countries, even they go for higher replacement. So why it's not adopted here? Because if they adopt more, it will be economical also, and
Very,
sustainability,
very nice.
environment
Well,
friendly also.
let me give you a very clear explanation how it is going. Dekho, fly ash is coming from what sources? Fly ash coming is from two sources. First one is power plant. Power plant, it is again bifurcated in two parts. It's AFBC and it's CFBC. It's coal based, it's husk based. One it is coming from direct reduction process, another is coming from coal based power plant. Okay. So whatever cement, whatever fly ash used by cement plant, it comes from the coal based power plants only. The ash which you are getting from kiln waste heat recovery boilers is not of that quality because it contains iron particles also. That's why cement companies are not preferring to take fly ash which contains iron particles. So major consumption, major part of the fly ash comes with coal based only. That's why the consumption has this variation. And so far as replacement is concerned, it depends on the binding properties of the cement, how they are creating it. That is the mixture, that is the combination of their product, how they go combined for it.
Thank you, sir. Why I asked this question, because recently one of my friends is working in industry, and
Okay.
there was a mass concrete, very huge concreting for raft foundations, and
Uh-huh.
then they wanted heat of hydration to be within certain limit, and
Okay.
then that heat of hydration was within certain limit when they were increasing it to 40 to 45%. But the
Okay.
authority was not allowing it on the context of IS code. So again, there is a conflicting. Because
Yes, yes,
you know
definitely.
that.
Nowadays, one more development is that fly ash are now being used in highways also. Earlier, it was not so approved, but now highways are also taking the bed ash material and they are using it. Earlier, they were not allowing it, but nowadays, highway, since filling material is not available in abundance, so highways are also using. Even the Bilaspur highway, they are using it, the fly ash. They have taken up the entire material here. So this is one more use which has come up.
Okay, sir. Thank you very much for your.
Thank
Thank you.
you. So nice of you. And again, I thank to entire team of NIT and everyone else, everyone participating in this program. So nice to give an opportunity to share my views. Thank you very much.
Uh, any more question? If you have, you can ask to sir. And recently, IS 456 here 2025. Here it is mentioned that fly ash we can use up to 35% in RCC also. So this is
Yes,
also
it is the
recent.
recent development.
Yeah,
Yes.
recent only. It is not published maybe.
No, IS
In
456 2000 is the latest, no? 2025
no, no,
come?
no. Yeah,
Uh,
25 draft was came.
no, but as per my knowledge, 35% is even in the, is it more than 35% or 35% only?
No, IS now it is mentioned 35%.
I think some of the foreign courts, they even go beyond 35%, I think. So,
No, in 25 it was already changed that our steel also and our that cement properties also, yeah, mineral admixture, whatever we are adding. So that draft is also with me. I will share with you also. And if
please share.
yeah, any
Please share the
question?
draft. If
Yes, yes,
possible,
yes.
please share the draft, please. Okay.
Yeah, yeah. Any question you can ask to sir also. Sir is here. Sir, you are here, no?
Yeah, yeah, I'm
Left.
available.
Yeah. You may ask to sir. Field people are not with us, so we can ask him.
Sir, I want to ask about the flash and JBS price. Hello.
Ma'am, your voice is not clear.
Hello.
Hello, yes, ma'am.
about the price of and GGBS.
Ma'am, you are asking price of GGVFS? Hello?
Yes, ma'am. Yes, ma'am.
Oh, yeah. Sorry. She is asking about the price of GGBFS.
The prices, it depends on the purchase department. That is the commercial requirement. How much quantity you need, what is the value? It can be finalized here. It is
For research purpose, steel plant people are giving free of
for,
cost.
for research purpose, you can take up at any point. It's not at all a problem. We can provide you.
Okay, sir.
Hello,
Actually,
sir.
we are working on Flash and GGBS, and
You
when
can
we purchased it,
you can take the both for whatever you need. You can take it. You can take fly ash as well as slag. You can both. You can take it. Even we can provide you beneficiation waste also. That is also available. You can do research on it. No problem. We can provide you samples.
okay, sir. Thank you, sir.
Thank you very much.
Hello, sir.
Yes, sir.
Sir, is there any practical application on steel slab pavements in India, sir?
Yes. It is being used in roads. It's a very good replacement of sand. Even we are using in plaster, tiles fixing, all those things. We are using it in backfilling. Very nice material. Base preparation, good enough. Even concrete has been for concrete. I think aggregate portion also it is there. We have replaced 30 to 35% of aggregates also. Both sand and aggregates it has been replaced. And it is
And
documents are also available.
Okay, sir. Sir, and one more question, sir. Is the friction between vehicle wheel to that steel slab pavement whether might be good or not, sir?
No problem at all.
Okay.
No problem. It's as good as what you are using it. It's a good concrete as well as for asphalt also. It's a good material. No problem with it. It's a replacement basically. It's not 100% replacement. It's a replacement in some
Okay.
percentages.
Okay, sir.
In sand, it's 80%, 70%, 60%. For some say if you are going for a tile fixing job, you can go for 100% sand replacement. It's there. We are using it. For concrete, you can go for 60 to 30, 60 to I think 50 to 60% replacement. You can get it in case of concrete also. It's basically a replacement. It's not a complete removal.
Okay.
You have to add materials along with that also.
But sir, but in foreign countries they may lead complete steel slab payments. I saw one
See,
article.
again, let me be very clear. Steel slags are in two categories. First one is slag coming up from induction furnaces. Second one is slag coming from blast furnaces. The steel, the material, whatever foreign countries are using, they are coming from blast furnaces, not from induction furnaces of in India. In India, induction furnaces is a major role. But in foreign countries, they go with the blast furnace process. In that, you can replace with the say road practices only. Even Tata's they are using it. In Tata, they are using it for road constructions also. Professor Satish is being doing this practice from I think last 10 to 12 years.
Hello, sir.
Yes, sir.
Sir, good evening. My name is Tejas Padalkar. Sir, my basic question is for increasing GGBFS as a replacement to OPC in concrete as a binder, minimum glass content is required. So, how much minimum glass content is required? We came across the replacement level up to 40-50%, but we can go up to 70% also. So, my question is how.
Actually, this subject requires to be worked in first in theoretical part in labs. It should be tested out. Then only it can be implemented. If your pilot project is successful, then it can be done.
Right, sir. But how this glass content is increased in GGBFS?
You have to experiment it only. After that only it can be assured. It's 100%. way to experiment it only. You have to practice it. Actually, the major role for your product is your sizings, how you better size it. You can go with the screening, you can go with different kind of sieves. Unless until your sizing is being done in a proper way, after experiment only you can ensure that this sizing can be maintained. Whatever we maintain the size, it's from 10 mm to minus 10 mm. This is the size what we are available. So on base of that size, you have to design your product.
Okay, sir. Right, sir. Thank you. Thank you very much, sir.
Good evening, sir.
Good evening.
Sir, myself Prithviraj. Sir, my question is, in recent researchers having mentioned that ultra fine slag, that is after processed from GGBS.
Right.
But also in India, it is named as another name as alcofine. Is it correct, sir? And also I'm
See. There are two parts. Main is your particle sizing, how you are doing it. Once you get the size, once you get the product, it is free from metals. Now it is in your hand. How you want to crush it. 100% it is up to you. How you want to use it, how you want to crush it. And all the things are available. Now, once you pass your material through high gloss magnetic separator, the percentage of steel, that is percentage of iron, Fe percentage, is reduces to nearly 3 to 5% only, which is not recoverable. So after that, it is coming in lumps, it is coming in fines form, it is coming in ultra fine forms also. So now it is up to you how you can use it. Now it is 100% in your hand how you can utilize it. You get the product is available. How to use it, that will depend on you.
okay, sir. And one more question, sir. I have to clarify this doubt, sir. In some research papers, it is mentioned that ultrafine slag, that is alcofine, is derived from the byproduct of glass manufacturing. Is it correct, sir? Or it is a byproduct of slag, that is in steel? I want to clarify this, sir.
No, it is from glass particles only. That is from some other industries, not from us.
Okay, so then GGBS, that is alcofine, and GGBS is separate byproducts.
Yes.
Oh, okay, sir. Thank you, sir.
Hello, sir.
Yes, sir.
I'm Dr. Dada Patil from Bombay. Actually, I had asked a couple of questions few minutes back. So this was really very nice session. Can I be in your touch for some, because I have done my PhD in concrete only. So maybe in future I will be in your touch. So very informative.
Definitely. My link is available. You can call me also. No issues. Even if
Okay,
you can visit Raipur, you can come to me also.
Yes, sir. Yes, sir. Definitely. Very nice lecture, sir. Thank you.
Any more question? Okay, sir. Maybe no question. They will.
Okay. Thank you very much.
Thank you very much, sir, for
Again,
your nice information.
Nice session, sir.
Thank
Nice
you,
session.
ma'am. Thank you.
Tomorrow again we'll meet at 6 p.m. and everybody should attend the session because 80% attendance is required for your certificate. Thank you. Good day. And this is my information that whenever session is started, we will take photo session also. This is required for Atal also. So you may on your video. And that one is in recording.
Noted, ma'am.
Hello? Okay, so from tomorrow onwards, we'll make it.
Ma'am, throughout the session, it is required to turn on the camera, or once in a while it is okay?
So whenever we'll say that for 1 minute, 2 minutes only, we have to on the camera and we'll take the photo and we'll turn off the camera.
Okay,
Is it okay,
ma'am.
no?
Yeah, yeah,
Is it
ma'am.
okay?
It is fine.
Okay.
Thank you.
Okay. Good night to all of you.
Good night, ma'am. Good night.
Good night.
Good night.